Hey there. We're surrounded by AI every single day. But have you ever stopped to think about what's actually pulling the strings? Well, today we're going to peek behind the curtain and meet the real engines of AI, the core algorithms.
Think about it. How does your phone finish your sentences? Or how does your favorite streaming service just know what movie you want to watch next? It feels kind of like magic, right? But it's not. And it's definitely not some single giant computer brain somewhere making all these calls.
The secret? Well, it's more like a whole team of problem solvers, a whole cast of characters, really. And each one is a specialist with its own unique way of thinking, its own personality, for handling different types of jobs. So buckle up. Over the next few minutes, we're going to meet these stars of the show. We're going to see how they tick and how they work together to make our lives just a little bit smarter. Let's dive in. Okay, so first things first, when we say a machine learns, what do we actually mean by that? Because it's a huge shift from the old way of doing things. So here's the key difference. With old school programming, you had to write out every single rule, step by step. If this, then that. But machine learning? It totally flips that on its head. Instead of giving it rules, you just give it a ton of data, loads of examples, and you tell it, go figure out the pattern yourself. And that learning process, it pretty much always follows the same basic steps. First, it chows down on a bunch of data. Then, it tries to build a kind of mental model of what that data looks like. And finally, it just keeps tweaking that model again and again, trying to get better and make fewer mistakes. It's this constant cycle of getting a little bit smarter each time.
All right, let's meet the first two characters on our team. These are kind of the fundamental building blocks. They're simple, but don't let that fool you. They are incredibly powerful.
First up, we have linear regression. Let's call this one the line drawer. So imagine you've got a chart with a bunch of dots showing ice cream sales on different hot days. This algorithm's only job is to draw the perfect straight line right through the middle of those dots. That's it. And once you have that line, you can predict sales for any temperature. It's kind of the hello world of machine learning. Next on our roster is the decision tree, or as I like to call it, the question asker. This one is super intuitive. It literally works like a flowchart or a game of 20 questions. A bank might use it for a loan. It asks, is their income over 50K? Yes. Okay, is their credit history more than 5 years old? No. It just follows this simple yes or no path until it lands on a final answer. Super clear, super easy to understand. Now, these individual algorithms are pretty smart on their own, but the real magic, the real power, happens when they start working together as a team. This is where things get really interesting. See, here's the thing. A single decision tree, it can get a little obsessive. It's kind of like a student who just memorizes the exact answers for one practice test, but has no idea how to solve the problems. We call this overfitting. It knows the training data perfectly, but you throw a new, slightly different problem at it, and it just completely falls apart. So, if one expert can be wrong, what do? You get a second opinion. Or in this case, a whole forest of them. And that brings us to our next big player, the random forest. This is the ultimate team player. Instead of relying on one single decision tree, it creates hundreds, sometimes thousands of them, and each one is a little bit different. Then, when a problem comes along, they all get a vote. It's the wisdom of the crowd. This teamwork cancels out the weird mistakes any single tree might make, which is why it's so incredibly good at tough jobs, like spotting fraud or even finding cancerous cells. But that's not the only way to play as a team. Meet gradient boosting, which I call the error corrector. Now, instead of everyone voting at once, this is more like an assembly line. The first model makes a prediction. The second model looks at the first one's mistakes and tries to fix just those. Then the third model fixes the second one's mistakes, and so on. Each one learns from the last, getting progressively better. This step-by-step improvement is why it absolutely dominates in data science competitions. Okay, so we've met the building blocks and the team players. Now let's bring in a couple of the advanced specialists. These guys have some really unique tricks up their sleeves. This is the Support Vector Machine, or SVM for short. We'll call it the Boundary Maximizer. Okay, imagine you have two groups of dots on a page, say spam emails and not spam emails. An SVM doesn't just want to draw a line between them. No, Its whole mission is to find the single best line that separates the two groups.
And here's what makes it so smart. See, lots of lines could separate the data, but the SVM looks for the one line that creates the biggest possible empty space, the widest possible no man's land between the two groups. It maximizes that margin, and that big buffer zone makes it way more confident and reliable when a new piece of data shows up that's kind of close to the middle. And of course, we have to talk about the superstar, the neural network, our brain mimic. The best way to think about this one is like building with Legos. The first few layers of the network, they learn to see the most basic little Lego bricks. Simple things like an edge, a corner, or a patch of color. Then, the next layers learn how to put those bricks together to make slightly bigger things, like a wheel or a window. The deeper you go, the more complex it gets. Those wheels and windows become a car, then a whole street scene. This ability to build complex ideas from simple parts is what powers pretty much everything, from facial recognition to real-time translation.
Okay, so everything we've talked about so far has a common theme. We gave the machine labeled data. We told it, this is a cat, this is a dog. But what happens when you have a mountain of data and no labels at all?
Well, that's a job for K-means clustering, our group organizer. You can just dump a huge, messy pile of data on it, say a list of what all your customers have bought, and it will automatically sort them into natural groups. It just figures out on its own who the similar people are. It's fantastic for finding hidden patterns, like figuring out different types of shoppers or spotting weird, unusual activity on a network. So there you have it. You've met the team, and the biggest lesson here is that there's no one-size-fits-all solution. The secret to good machine learning is knowing the strengths and weaknesses of each of these players and picking the right one for the job. So let's do a super quick rundown. For simple predictions where you need to know why, you grab the line drawer, linear regression. For clear flowchart-style decisions, you want the question asker, the decision tree. When you just need raw accuracy, you call in the team player, the random forest. For separating complex data, the boundary maximizer, SVM, is your specialist. And for finding those deep, intricate patterns in huge amounts of data, nothing beats the brain mimic, the neural network.
And really, that's the whole point. As AI gets more and more woven into our lives, the real skill isn't just using these tools, it's understanding why they work the way they do. Because when you get the why behind the what, that's when you can really start to shape what comes next. Thanks so much for joining us.